So the last section in chapter 2 is about measures of position. Section 2.3 and 2.4 were about summarizing entire data sets, like 2.3's measures of center, where the center is of an entire data set. 2.4 is the measure of spread, what is the spread of an entire data set. But 2.5 is a little different because it's still a measurement, but now we're going to talk about the measurements of the location of data entries in a data set. And you probably are familiar with many of these measurements before, but we're going to talk in them as we normally do in more detail, and you'll probably understand how they're used more. Or you may even see how they're incorrectly used sometimes. So the first type of measured position we're going to talk about is a fractile. And fractiles are numbers that partition or divide an ordered data set into equal parts. One of the more common fractiles are quartiles. And quartiles are denoted by Q1, Q2, and Q3. So there's 3 quartiles, which divide a data set into 4 parts. And some people ask themselves, well, aren't they quartiles? So why is there only 3 of them? Well, it's because it divides a data set into 4 parts. So one way to think of this is, if this is, let's say, a board, and you're trying to cut the board, okay, the quartiles, Q2 is in the middle, and then Q1 and Q3 are on either side. And the quartiles mark the cuts in the data set or the board for this analogy. But there are still 4 sections, right? So that is why they're called quartiles, because it divides the data set into 4 parts, but there really only needs to be 3 cuts to make that division. And Q2 is also known as the median. So that is usually what we find first. We have a data set here, and we're going to practice this, of 15 test scores of CPR for a CPR training course, and we want to find the quartiles of the data set. So similar to find the median, it's always most helpful to order the data set from least to greatest. So that's what I'm going to do. 5, 7, 9, and I'll just do this for you. I think you're capable of ordering a data set from least to greatest. So 5, 7, 9, 10, 11, 13, 14, 15, 16, and I'll go down here, 17, 18, 18, 20, 21, and 37. And we want to find the quartile. So the first quartile you're going to find is the median because it's the easiest, and the median is the middle number. So if you follow this data set, there's 15 employees, which means the 8th number is the middle number. 1, 2, 3, 4, 5, 6, 7, 8. So it looks like 15 is our median, which is Q2. Okay. And then 10 is Q1 because that is the median. Basically, the first quartile is the median of the lower half. Now, when you find the median of the lower half, make sure the half doesn't include Q2. And there's actually a couple ways to do this, but for our purposes, we're not going to include the median. So if the median is an actual data value, don't include it. So the median from 5 to 14 is 10, and the median from 16 to 37 is 18, which is Q3. And it's the second 18, by the way. And so those are our quartiles. Now to find, or one purpose of quartiles, I should say, is calculating the interquartile range. And a couple sections ago, I talked about outliers. And outliers were a way to, or outliers were data values that were far away from the rest of the data. Well, interquartile range, which is the difference between the third and the first quartile. So if I take Q3 and subtract Q1, that is what we call the interquartile range. And you can use this interquartile range as a rule to find outliers. And this bullet point describes to you how you can use the interquartile range to find outliers. So let's just see if there's any outliers in this data set here. And by looking at it, if we look at our ends of our data set, we see 37 is pretty far away from 21, so that is probably an outlier. And 5 isn't really far away from 7. So let's see if our rule makes 37 an outlier or not. So to calculate if you have an outlier or not, we take our quartile, so our first quartile, and we subtract 1.5 times the IQR. And we take our third quartile, which is the upper end, and we add 1.5 times the IQR. So just a note here for this problem, the IQR is the third quartile minus the first quartile, which is going to be 18 minus 10, right? Because 18 was our third and 10 was our first. So, So it looks like our interquartile range is 8. So we're going to take our first quartile, which is 10, and we're going to subtract 1.5 times 8, which is negative 2. And we'll do the same thing for the third quartile, but we'll use 18. Which is 30. So if you look at negative 2 and 30, what you want to ask yourself now is, are there any numbers in our data set that are outside those values or outside that range? If there's a value in our data set that is below negative 2 or above 30, that is considered an outlier. And there's no values below negative 2, but indeed 37 is above 30. So we can say, therefore, I'll use our common 3 dots for therefore, 37 is an outlier. Okay. And that's how you can find outliers using interquartile range. Later we'll talk about another way to find outliers as well, but this is one of the methods that you can use. Also, the quartiles give you something called a 5-number summary. And the 5-number summary summarizes a data set. And instead of just using a couple values, it uses 5 values in a data set that show about the general spread. So for example, the 5-number summary goes like this. We list the minimum, the 3 quartiles, and the maximum. So our 5-number summary, it would be 5 because that's the smallest value in our data set. Our quartiles are 10, 15, and 18. And our maximum value is 37. So if I were to ask for the 5-number summary or what the 5-number summary is for this data set, that's what it would be. You can represent a 5-number data set graphically, or 5-number summary graphically, by using a plot called a box and whisker plot. So yet again, another graph that we can use. And a box and whisker plot has a title. So test scores of CPR class, so we'll still use our CPR data. And as always, we have a title. And our lowest score was 7, right? Or no, 5. So we'll just start. Just make a couple tack marks here. Start at 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay, so to make a box and whisker plot, what you do is you make the box first. And the box is made up of the quartiles. So we start with the first quartile, which was 10. And we put a line, a vertical line. And then our second quartile was 15, and we'll put a vertical line at 15. And our third quartile was 18, so we'll put a vertical line at 18. And this makes up our box. So again, this is the first quartile, second quartile, and third quartile. And then the whiskers come out from the box. So in this direction, this is our minimum, and so this is our first whisker. And then our second whisker on the right side goes out to 37. Now, because 37 was an outlier though, we're going to actually put like a little asterisk here, and that identifies what the outlier is. But the second highest data value, if you go back to our data set, was 21. So our whisker is actually going to only go out to 21, and that's just because 37 was an outlier. So this way, because if I had this long whisker that went out, it looks like there's a lot of data that's spread out, from 18 to 35. But that's really not the case. Really, most of our data in this upper fourth here, or this upper quartile, is just from 18 to 21, and there's only one data value that's really out here. So I like this method of a box and whisker plot of identifying outliers this way. And remember that when you identify outlier, or when you create a box and whisker plot, each of these are 25%, each of these sections. And this is nice because the 25% of the data should be within each fourth. And so if you have like a point that's close to a line, that data is much more concentrated here. There's a lot of values there. But if you have a data that's more spread out, well, that means that there's just as many values in between the values that are more spread out, and so the data is more spread out there. So it kind of gives you what a general shape of the data looks like, which is why a box and whisker plot can be considered useful. So that was quartiles, and there are other types of fractiles as well. So what we've just discussed were quartiles, and it divides a data set into 4 equal parts, and we use Q1, Q2, and Q3 to find these quartiles. There are also something called deciles, which divides a data set into 10 equal parts, and that's D1, D2 all the way to, and just like quartiles, divides a data set into 10 parts, but there's really only 9 deciles. And the last one is probably the one that you've heard before. If you haven't heard of quartiles, you've probably heard of percentiles though. And percentiles divide a data set into 100 equal parts, and that's P1, P2, all the way to P99. And this is an important thing I want to mention here, which is that there is no 100th percentile, right? Because the percentile is really just the cut that's made in the data set to divide the data set into 100 equal parts. But there really is no 100th percentile. So if you ever get like your test scores back, like let's say you take the SAT or PSAT, it tells you what percentile you're in for that standardized test. And that standardized test will never put you in the 100th percentile because it doesn't exist. My son, his head size was like in the 99.7 percentile, and the doctor actually said his head size was in the 100th percentile, and that bothered me because I knew that that wasn't possible, but I let it go because, he's taking care of my son. But yeah, so, and yes, he does have a big head. But anyway, percentiles, basically, if you're in a percentile, what that means is, like if you're in the 87th percentile for weight, that means you weigh more than 87% of all individuals in the population or sample, depending on, I'll say /sample, depending on what you're talking about. And also, the percentile just allows you to be more accurate. So the 25th percentile is the first quartile, the 50th percentile is the second quartile, which is also known as the median, remember, and the 75th percentile is the third quartile. And those are the, that's basically percentiles. So because percentiles are used so often, I think it's useful to talk about them a little more. And to find a percentile for a data set, what you can do is we can take the number of data points less than x, or less than the number that we want to find the percentile of, and we divide by the sample size or population size, depending on what we're talking about, and then we multiply that by 100. So let's look back at the CPR scores that we're talking about, and let's ask ourselves what the percentile corresponds to a score of 18. So if we go back, we want to find the percentile that corresponds to a score of 18. So how many data points are less than 18? Now remember, is 18 less than 18? No. So we have to count everything that's less than 18. And this is exactly why you can never be in the 100th percentile, because if you even score on the very top of something, like let's say you're this 37. If I want to find the percentile for 37, I don't count 37. I count everything beneath it, which there would be 14 data points beneath it because there's 15 employees total. But going back to the 18, how many are less than 18? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like 10 values or 10 scores are less than 18. So we'll go all the way back down here. So that's 10, and we divide by the total number that we have, or the sample size, which is 15, and we multiply by 100. And that gets us 67 after rounding, which is the 67th percentile. So you can write the percentile out like this, or you can write capital P sub 67. What you should not do, though, is write 67%. This is a no-no, because 67% is actually a percentage, whereas percentile is not a percentage. So make sure that you do not put the percent sign in the percent when you give a percentile. So go back to your CPR data set and see if you can find the percentile for a score of 20 on your own. So hopefully you found the percentile of a score of 20 on your own, and when you did that, you should have found that there were 12 data points that were less than 20 divided by 15 times 100, and this got you 80. So again, you can write 80th percentile or P sub 80. And that basically summarizes percentile. The last measurement of position, and this measurement we're going to actually use a lot more of, especially in chapter 5, but it's called z-scores. And a z-score basically tells you how many standard deviations you're away from the mean. So in the previous section we talked about standard deviation and how to calculate standard deviation. And because standard deviation is a measurement of spread, you can compare data sets by just finding out what the z-score is for certain data values in different data sets. Because a z-score basically standardizes the data. So to find a z-score, we use our data entry that we want to find the z-score for. We subtract the mean, which is mu, and we divide by our standard deviation, which is sigma. If you have this is for population, by the way, if you have a sample, you subtract x bar and divide by s, right? Because x bar is the sample mean and s is the sample standard deviation. Okay, so let's actually use this z-score and we'll interpret what it means. I think after you see a couple examples, it'll be a little bit more clear to you. So this first z-score is the mean speed of vehicles on a stretch of highway is 56 miles per hour. So that's important because that's the mean speed. And a standard deviation is 4 miles per hour. So we definitely need those two things. And you want to measure the speed of 3 cars along the stretch of highway. You get 62, 47, and 56 miles per hour for those speeds. And we're asked to find the z-score that corresponds to each speed. And what can you conclude? So 62, 47, and 56. So to find the z-score, it's x minus mu over sigma, which is 62 minus the mean, which is 56, over 4, which is 1.5 when we calculate that. So this speed, this vehicle in particular, is driving at a speed that is 1.5 standard deviations above the mean, which is pretty far above the mean. There's not many data values. I mean, that's probably the top, I don't know, let's say the top maybe third of the data, maybe a little bit higher than that. So like maybe the top fourth of the data would be in the top 1.5 standard deviations above the mean. Depends the shape of the data too. But so this person is definitely going faster than average, because a z-score of 0 means you're not away from the mean at all. A z-score of 0 means you're 0 standard deviations away from the mean, and you're going average, right, an average speed. So try to find the z-score for 47 and 56 miles per hour on your own. And pause the video here. So hopefully you found the z-score for 47 and 56 miles per hour. The z-score for 47 miles per hour is going to be 47 minus 56 over 4. And this z-score is negative 2.25, so that's going to be a really slow car. And then the z-score for 56 miles per hour, and really you don't even need to use the formula because 56 is the mean. So your numerator is going to be 0, so your z-score is just 0 because you're not away from the mean at all. Okay, so let's think about this a little bit. It says 62 miles per hour is 1.5 standard deviations above the mean. 47 miles per hour is negative 2.25 standard deviations away from the mean. That means that's going really slow. That's 2 standard deviations below the mean. That's like your grandma on the road, right? Or maybe it's like a truck that's hauling something really large. There's not many vehicles on the road that go that slow. And then a z-score of 0 is average. They're just going with the traffic, going with the flow, and that's it. And if you have a data point and you find a z-score and it has more than 2 standard deviations away, we can call this unusual or an outlier. And 47 miles per hour is unusual or an outlier because it is more than 2 standard deviations from the mean. Okay, so z-score is a very useful concept because it helps you see how far a data value is away from the mean in the data set that you have. So it takes into account center, it takes into account spread, and it takes into account where that data point is located, and it's very useful to compare data sets. To give you an example of this, the last 2 examples we'll do in section 2.5 are related to actually using z-scores to compare data sets. And we're going to talk about test scores. And to kind of give you an example of this before we read this example, like let's say you are comparing with a friend, and let's say you're taking a really hard physics test, and in physics let's say you ended up getting a B on this physics test, and everybody else just did awful on it, but you got the top score, you got a B, okay? And then let's say that your friend who you're talking to is like, well, that's okay, but I got an A on my health test. And everybody else pretty much got an A or a B on this health test. Like, it wasn't hard to get an A, but they still got an A on it, right? And so technically they got a better grade than you, right? They got an A and you got a B. So which one got the higher score? Which one got a better score? Well, I mean, if you just compare like the actual score at face value, well, they got the higher score, right? But really, you know that this physics test was a lot harder, and you want to compare apples to apples, right? You want to see, well, how, based on the difficulty of the test, how difficult is this test? Because, I mean, it's a health test, right? It's not difficult at all. Physics is generally considered a lot more difficult than health for pretty much everybody, I think, on the planet. So with that in mind, you can use z-scores to compare these. So if you knew the standard deviation and the mean of the groups that took the respective tests, you can calculate the z-scores and then compare the z-scores. So with that being said, let's look at the z-score for the statistics test and the z-score for the biology test. So let's do this example. We have, for the statistics test scores in a class, the mean is 63. Oops. For the statistics test scores in the class, the mean is 63 and the standard deviation is 7. And the biology test scores in a different class, the mean is 23 and the standard deviation is 3.9. So we want to find the z-score for the statistics test. So I'll just put a subscript s here just to say that that's the z-score for the statistics test. So that would be 73 minus the mean, which is 63 for the statistics test, divided by 7. And the z-score for that is about 1.43. And we'll do the same thing for the biology test, which is 26 minus the mean, which is 23 over 3.9. And this z-score is 0.77. So if we're comparing these, which test did the student do better on? Well, it's the statistics test because it has the higher z-score. So the student did better on the statistics test. And one thing I want to point out, and I'll write it down I think as well, this is relative to the rest of the class, right? Because once again, at face value, like 73, that could be 100%. I don't know. Or the biology test, it could be 100. 26 could be 100%. But if everybody else did better on it than the statistics test might actually be the harder test. So this takes into account how everybody else did and what their scores are. So try to find the z-score for the part B. Pause the video here and then do it on your own and compare the z-scores. So hopefully you found the z-scores for the statistics test. The z-score for this statistics test is 0, and the z-score for the biology test is 0, because both of these z-scores are the mean, right? 63 is the mean. So you have 63 minus 63 and 23 minus 23 on the top. And so they're not only the same z-score, they have they also scored average. So the student did equally well on both tests. All right, and that's section 2.5, which wraps up all of the chapter 2 contents.